In the previous video, I introduced the idea of stable and unstable equilibrium points. By considering several examples, we saw that feedback loops are related to the stability of equilibrium points. In this video, we'll further investigate feedback strength to be able to better analyze the interplay of feedback loops and equilibria. The strength of a control is a measure of how much the flow is affected by a small change in stock. To compute this, we measure the change in flow that results from a small change in the stock and take the ratio. Note that the units are flow units divided by stock units. We can think of this as a percent per unit time. For an exponential model, the strength is equivalent to the constant percent change of the feedback loop. For example, consider a population model. Both the births and deaths create direct feedback loops. Suppose the strength of the birth feedback loop is 0.05 with a time unit of years. This means that births increase the population by 5% per year. The death control arrow has a strength of 0.03. Since this feedback loop is negative, this indicates that deaths remove 3% of the population per year. We can determine the net effect of the stock by simply adding the strengths. In this model, the population is growing by 2% per year. Let's look at an example where the strength is not constant, the logistic model. Here, I've shown the flow equation, a plot of the stock versus flow, and a plot of the stock over time. For this model, the rate constant is 0.035 and the carrying capacity is 6,000. First, let's measure the strength of the flow at point A. The stock level at this point is 1,500. Using the flow equation, we can compute the flow at this stock level. So we get F0 is equal to 0.035 times 1,500 times 1 minus 1,500 over 6,000. This comes out to be 39.375. If we move to a slightly higher stock level, say 1,510, we get a flow F1 of 39.549. Then the strength of this control arrow will be the difference in flow levels, so 39.549 minus 39.375 over 1,510 minus 1,500. This comes out to be 0.017. This shows that at this stock level, the overall feedback is amplifying. Viewing this on the stock versus time plot, this corresponds to the curve accelerating at this point. Doing the same calculation at the point B, we get a strength of minus 0.006. This shows that at this stock level, the overall feedback is stabilizing. On the stock versus time plots, this corresponds to the stock growth starting to slow down. For those of you who have taken calculus, this calculation may look familiar. In fact, it's a version of the derivative. We can apply this same type of analysis to the phosphorus example we considered earlier. Let's analyze the feedback at the equilibrium point. Note that the outflow increases at a constant rate with respect to the stock. The strength of this is just the slope of the line, or 0.5. This contributes a strength of minus 0.5 to the system, since this is a negative or stabilizing feedback loop. The inflow feedback loop is amplifying. I've calculated that the inflow at this point has a strength of approximately 0.2. Therefore, the overall strength at this point is 0.2 minus 0.5, or minus 0.3. This shows that the overall feedback at this point is negative, resulting in a stabilizing effect. In other words, the outflow feedback loop is stronger than the inflow feedback loop at this point, so the net effect is stabilizing. This suggests that the equilibrium is stable, consistent with my analysis in video 1.